In today's lesson, we're going to look at linear programming. This may be a new topic to most of us. And linear programming, it's a method that we're going to use to find minimum and maximum values of some quantity given a set of constraints. Now, constraints are defined to be the inequalities that limit the problem given to us. We're going to find a feasible region, and a feasible region is a shaded polygon created by the intersection of graphs of inequalities. So it's going to look like a system of inequalities when we solve linear programming questions. And then we're going to be given an objective function. It'll be a function in two variables, both x and y. And that objective function will give us maximum and minimum values. It's used in business like profit from sales and such. And you can have an unbounded region by having a function where there's no maximum value, and the shaded region of the constraints don't form that closed figure of a polygon. So let's jump in and look at some of these situations. We're going to be using the property called vertex principle of linear programming. And that property says if there is a maximum or a minimum value of a linear objective function, it has to happen at one of the vertices of that polygon region called the feasible region. And I've come up with 5 steps for how we can go about sketching that feasible region. Now, in the first step, we're going to want to graph each inequality on a coordinate axis system. So let's look here at example number 1, where we're going to graph. So we have x is greater than or equal to 3. So I know if I come up here, 1, 2, 3, 4, 5. We'll say this is 5, 6, 7, 8, 9, 10. And we can do the same thing on the axis, x-axis. 1, 2, 3, 4. We'll make this 5, 6, 7, 8, 9, and this 10. So if x is greater than or equal to 3, we're going to go on the x-axis at 3 and draw that vertical line. X is greater than or equal to 3. And what I like to do with these cases is I like to take a little mark and put an arrow that I would shade to the right of this line. So that takes care of equation 1. Now equation 2, I want y greater than or equal to 2. So y is greater than or equal to 2 along this horizontal line. And again, put a little mark up here. I want to shade up to be greater than. In the third equation, y is less than or equal to 7. So if this is 10, 9, 8, 7, so y is less than or equal to 7. In this case, we would be shading down. And then in our fourth equation, we need to do a little bit of algebra. All the numbers that add up to 10, two numbers, x and y, that add up to 10, would be y is less than or equal to negative x plus 10. So we're going to have a solid line going down from 10 across this way with a negative 1 slope, and it would meet up on the x-axis with 10. And then again, placing my little red mark to shade below that, you can see that where these intersect, we're going to have this little triangular region in here is the polygon, and this polygon happens to be a triangle. So in our polygon region, that's known as our feasible region. It's this portion that's known as our feasible region. In that feasible region, we need to know where the vertices are. So that would have been step 3, the vertex here, and here, and here. So this vertex is the ordered pair 3, 7. This is the ordered pair 8, 2. And then this third one is the ordered pair 3, 2. Now in this example, we don't have the objective function to finish steps 4 and steps 5, but we'll see that in our next example. Now in example 2, we're going to solve a problem using linear programming, and then you can see down here we do have an objective function that we'll use to find the maximum and the minimum of our feasible region. So I've pre-solved the first equation. We want to graph y is negative 1/2 x plus 4.5. So to make this easy for us, I'm going to use my y scale as every line is a half, which will give us enough to graph this fraction of 4.5. And doing the same thing on the x-axis, this skipping each line as a half would give us a nice even graphing. So at 4.5, we want to start here and go 1 down and 2 right with that negative 1/2 slope. That would be a straight line, and we want to shade below that line. So I'm going to put a little mark that I'm shading below that line. The second equation is greater than or equal to x minus 3. Now I don't have negative 3 down here, but I know if I have a 4, when you substitute 4 into the equation, 4 minus 3 is 1. So I could start with the ordered pair 4, 1 and have a slope of 1 going off this way. So we would have that line there, and you would want to shade above that line. So our arrow would point this way. Then we don't need to have the y-axis going down to negative 3. In the third equation, x is greater than or equal to 0, which means the y-axis in this case. So we're blocked off by the y-axis because x is greater than or equal to 0 to the right. And then y is greater than or equal to 1 is a horizontal line at 1, and we would shade above. So jumping over to our highlighter, we're going to shade to the right of the y-axis above 1, and we're making this 4-sided polygon, irregular polygon here. Okay? And we need to know the vertices of our polygon. So I'm going to get rid of the little red arrows just to make our region a little cleaner. And we're looking for our feasible region. So that would be 0, 4.5, 0, 1. This one is 5, 2. And this ordered pair is 4, 1. So I like to make a table that's going to include those XY coordinates, 0, 1, 0, 4.5, 5, 2, and 4, 1. And then we're going to substitute those x and y values into our objective function, which is 3x plus y. So 3 times 0 plus 1 gives me 1. 3 times 0 plus 4.5 will give us 4.5. 3 times 5 plus 2 is going to produce 17. And 3 times 4 plus 1 is 13. And our final step in that procedure was to determine the maximum, which is the highest value, or the minimum, which would be the lowest value, by using substitution. So what point of the feasible region maximizes? So the question is asking us to maximize, and we can see the maximum value is 17. So the maximum AXI maximum. So the maximum occurs at the ordered pair 5, 2. This is the maximum, and the maximum value is 17. So we could say the maximum is 17 at the vertex 5, 2. The maximum is 17 at 5, 2. Now, if you think you have a good handle on this, I would suggest you turn the video off and try example 3 on your own. They've given us a set of inequalities, and we also have the objective function here. Your job will be to find the intersection points of the vertices for your graph -x plus 8 and the graph -2x plus 10. X greater than 0 and y greater than 0 are the x and y axis, and we could use the scale of 1 for each line on our grid here. So let me just number those. This would be 2, 4, 6, 8, 10, and then across x, 2, 4, 6, 8, and 10 here. The first line starts at 8 and has a -1 slope. The second line would be shading under that. The second line starts at 10 and has a -2 slope, so it's a little bit steeper, working down toward this x-axis right here, shading below that, and then like I said, we're shading to the right of 0 and above 0. So grabbing our green pen, we're making this polygon in here, and we're looking for the vertices of this polygon. So we have 0, 0 as a vertex, we have 0, 8 as a vertex, we have 2, 6, and we have 6, 0. So we have 4 ordered pairs that would be substituted into this objective function. So next I want to make a table that we can use for keeping our work organized. We have an x and y ordered pair for the vertices at 0, 0, 0, 8, 2, 6, and 6, 0. Or I'm sorry, not 6, 0, 5, 0 there. Don't let me mess up. And 5, 0. Oh yeah, this was 6 over here. And then our objective function is 100 times x plus 40 times y, and that would be our maximum or minimum. So in this case, we have 0 plus 0, so that's going to be a minimum. We have 0 plus 40 times 8 would be 320. We have 100 times 2 plus 40 times 6, so 440, and we have 100 times 5 plus 40 times 0, so 500. And the largest value, 500, is the maximum because it's asking us to maximize. So 500 is the maximum, and that occurs at the ordered pair 5, 0. Now we want to use linear programming in a more practical application. A baker earns 15-cent profit per glazed donut, G, and 40-cent profit per jelly donut, J. Do you see that's going to be our objective quantity right there? If a customer wants to buy no more than a dozen donuts and wants to try at least one of each kind, what's the maximum profit the baker can earn? So I'm going to use G for glazed and J for jelly. if they want to try one of each, that would be G plus J has to be less than or equal to 12 in a dozen. And G would be greater than or equal to 1, and J would be greater than or equal to 1, so that they could try one of each. Now our profit objective function is based on the money, 15 cents per glazed and 40 cents for every jelly. So graphing these along the X and Y axis, again, I'm using 1 mark. So 12 would be about here. And then the same thing on the X axis, where each tick line is 1 unit. So along the lines of adding up to 12, we're going to come down this way to add up to 12. So we'd be off the mark there. Needed a little bit bigger grid. And then greater than 1 on the jelly donuts, if jelly is up here, and glazed is our x-axis. So this is the G-axis and this is the J-axis. And greater than 1 along the glazed. So our shading is going to become a triangle inside of here. And then we want the vertices for our feasible region. So the vertices are going to be this ordered pair here, 11 on Y and 1 on X. Whoop, getting ahead of myself. So 1, 11. This one is going to be 11, 1. And this vertex would be 1, 1. So we're looking for a maximum profit. And our glazed and jelly vertices are 1, 1, 1, 11, and 11, 1. Our objective function is 15 cents per glazed, 40 cents per jelly, and that's going to give us our profit. So 15 times 1 plus 40 times 1 is going to be 55 cents profit. Then 15 times 1 plus 40 times 11 would be 455. I'm sorry. 455. And then 15 times 11 and 40 cents times 1 would give us $2.05. So 455 is our maximum profit, and we could write that in a sentence. We have a maximum profit. The maximum profit is $4.55 if the person buys 1 glazed donut and 11 jelly donuts. So that's pretty common sense. And then example 5, Josh has 40 minutes to complete a government exam. There are 12 multiple choice questions worth 5 points each, and there's also 5 short answer questions worth 8 points each. It takes about 2 minutes for Josh to answer the multiple choice questions, and we're using the letter M, and about 8 minutes to complete the short answer questions. Josh is trying to figure out how many of each type of question he should answer to maximize his score. So we have some constraints of time. So our time constraints are 2 minutes per multiple choice and 8 minutes per short answer, and they have to be under 40 minutes. And we have the constraint of the type of question, and he has less than 12 and on the multiple choice, and somewhere between 0 and 5 on the short answer. And on his score would be 5 times multiple choice and 8 times short answer. So if we graph that out, and the y-axis is our short answer, and the x-axis is our multiple choice, we've got one constraint at S is less in between 0 and 5, so we're shading down, and then we know this is 10, so we have to come out here to 12. So we have the multiple choice has to be between 0 and 12, and then starting at 5, we would solve 2m plus 8s is less than or equal to 40, so that's going to be, here we're going to go down 1 and right 4, because the slope here would be 1/4. Down 1 and right 4, down 1 and right 4, down 1 and right 4. So we're at 12, 2 here. And our line comes across that way. And we would be shading underneath that as well. So our feasible region is under this line, and we would want integer answers in there. And we need the vertices, so we have the origin 0, 0. We have 0, 5. So we're going to make a little table here, and our m and s values, since m is on the x-axis and s is on the y-axis. We have 0, 5, and 12, 2, and then 12, 0. So I'm going to leave off 0, 0 to save space. And then substituting 5m plus 8s for our score, 5 times 0 plus 8 times 5 is going to give us 40 for the score. So we had a score of 0, a score of 40, and then 12 times 5, that's 60, plus 8 times 2, that's 16, so we have a score of 76. And then 5 times 12, that's 60, and 8 times 0, that's a score of 60. So our maximum score would be 76, and the way he could get 76 would be to answer 12 multiple choice and 2 short answer. So I guess we could erase this up here and write that in a sentence, his maximum score. So we have that maximum score there. Then the last example, we have a small company has 3 ton trucks. There's 5 of them, and they have 4 5-ton trucks, and they're hauling gravel. But only 7 crews are available at any one time to operate the trucks. We want to know how many of each kind of truck should be used to haul the maximum amount of gravel per trip. We're letting X represent the 3-ton trucks. These are the 3-ton on this X-axis, and the Y-axis is representing the 5-ton trucks, and we have our objective quantity here. So the system is going to be the X truck plus the Y truck can't be more than 7 people at a time. X has to be less than or equal to 5, and Y has to be less than or equal to 4. So again, using a 1-to-1 ratio on our grid here at 7, we've got one line coming down across this way. We have X is greater than 5, or I'm sorry, x is less than 5, and y is less than or equal to 4. So the shaded feasible region is inside here. Our vertices are at the origin, 0, 4, 3, 4, 5, 2, and 5, 0. And our job is to find the maximum there. So our constraints look like x and y, and the objective quantity, and then the tons of gravel that they can haul. So 0, 0, again, is going to produce 0 tons. 0, 4 in our objective, 3 times 0 plus 5 times 4 is going to give us 20 tons they can haul. The next vertex is 3, 4, and 3, 4 is going to give us 3 times 3, that's 9, and 5 times 4 is 20, so we can tow 29 tons. The vertex at 5, 2 is 3 times 5, that's 15, and 5 times 2, that's 10, so 25 tons. And then the last one is 5 and 0, so 3 times 5 is 15, plus nothing, so 15 tons. And maximum is 29 tons. They would haul 29 tons if 3 small trucks and 4 large trucks are out on the job. That's the end of lesson 4 in chapter 3.